Okay, so I placed myself here on the left side of the screen. I realized last time that I just covered a lot of the stuff which was on the right side, because we are now pretty much here at the end. Results and thermal maps and so on. In my model, again, very quickly, so this was the original one. I'm almost thinking let's delete that for now. We don't really need that. And we're left with whatever is here. We did the balance, energy balance, and we did, in the last video, we looked at some of the outputs, like for example the phase indoor temperature, outdoor temperature, and energy flow. We also looked at other aspects of the data, like air temperature and radiation temperature, outside and inside the room, and so on, humidity. And there's still a little bit left. I also cleaned up the file a bit, where we have basically all the model stuff here, and then we have the weather data. I just made some relays where we can access the weather data a bit better, so we know this is weather data and this is the model which is coming out of here. And then I also cleaned up whatever we didn't need at that time. And then now we're gonna jump back into results. There was still some things missing which we haven't touched on. We looked at the comfort level. We looked at the energy level? I think we did. This was basically our energy levels. This is this one. We already touched that. And we looked at on how we use the face coloring and the room coloring, which basically colors the floor of the rooms. And then let's cover very quickly these bits. There's actually not so much to say about. Let's start with this. HB read tabular data. Basically another way to look at data, and specifically the tables which are created within the report. And you can access it by attaching here the SQL data, and then you can add a table name. Now, we don't know what kind of table names there are, but we can get that out of the HTML file. And if I added a panel here, I can access the HTML file. So we could just copy the data only, which is basically this link. You can go there. This is the HTML file, which is created when I create my Open Studio model. Then it also creates this HTML file with all the data, and every time it calculates its and I could, for example, now very simple site source and energy, or maybe building area. It's very simple. So we could take this and want to look at something very specific. Then we can get a panel and type the name in here of this building area and put it in here. And we already have our data in here. This basically reads the data out of the report or out of the model, and we can then look at the column name, the row names, and the values, which are the same as in the HTML file. 169 square meter. So pretty straightforward. Nothing more else to say. We did the balance already. Just remember that there are different types of balances. There's balance storage, the normal balance, and the normal balance storage. And please read what these means. They mean different things. Google it and try to research what these different outputs mean. But yeah, we looked at that already. There's another tool here. It's called Honeybee Balance Temperature. Here we need to add the data from the cooling, which we get out of these energy results, cooling and heating. The temperature I get from the weather data. This is the outdoor temperature. And the weather data, in order to access the temperature, we need to use Ladybug. And Ladybug has this tool here, import e plus weather data. And we can connect here the weather data. And that gives us the temperature, the dry pulp temperature. It's the outdoor temperature. And that gives me an output. And it says here, the average thermal load on the balance day. This number should be close to 0 if the balance temperature is accurate, and this output is meant to give you a sense of the accuracy of the balance temperature value. Okay, so the closer it is to 0, the more accurate. I think that means it's quite close to 0. It's 0.04. So I guess you could call this quite close, maybe. The balance temperature, the outdoor balance temperature. I guess this is the average outdoor temperature. Yeah, what else to say? I mean, please read. There's always like this very detailed description on what you actually do with it. So in that case, calculate the building balance temperature from a ideal air load simulation result. The balance point is the outdoor temperature at which a building switches between heating and cooling. If the outdoor temperature drops below the balance temperature, the building will usually be in heating mode, and if the outdoor temperature is above the balance temperature, the building will usually be in cooling mode. Balance temperature concept is useful for setting things such as automated blinds and airflow schedules, since having these things directly controlled by hourly cooling or heating demand isn't always straightforward. This component works by taking the average combined heating cooling values for each day and the average outdoor air temperature for each day. Days which with the smallest combined heating and cooling will have their daily mean outdoor air temperature averaged to produce the output balance temperature. So always read what's written here, and then if you don't understand, research online. What else? We need to go back here. The Honeybee energy. The Honeybee phase result by type. To be honest, I didn't got it to work. I think I would need to have select specific Honeybee. I would need to key specific items in the model in order to read this or separate the data to these different items. But it should be straightforward. If I have an identifier for the certain element I want to check, I guess that's how I try to understand it. I can input here the model first of all and the data. Let's go with the cooling again, or with the heating, it doesn't matter really. That gives me, it tells me it worked, but the thing is there is no specific output here. If you understand this better than me, then let me know. Again, it's something very specific where you can test just one specific surface or one specific item in your building. Let's not bother with it. If you know it better, how it works, let me know. I didn't really got it. Some things are not very logic, and they're not very described very well. But yeah, I'm not 100% sure how that works. So I don't know everything, and it's okay. Here, this is quite useful. It's normalized by floor area, so I could take the model here again as an input for everything, for all the data. And data would be, for example, I don't think I can just use this one, can I? Let's take the lighting. Continuous hourly data collection. Now this, I need to use a tool again, which we use quite often, is the Ladybug construct data, which divides the headers from the values. It's again, what is a bit annoying is that it's not 100%. I mean, there could be a bit more description of what it actually does, because normalized zone level data collections for an energy simulation by the floor area of the corresponding Honeybee rooms. By a normalized zone level data. Again, this is very abstract for me. I'm not sure exactly what that means. It's not perfect. Nothing's perfect, and I don't know everything. These two are actually quite interesting. Read result dictionary, and it's good. We can go here into the result data dictionary. And yesterday we discussed about the custom simulation output. Actually, it has something to do with that. So the custom simulation output, you can use your simulation output, for example, here. Here we have our typical simulation output, and this is like a customized output. It's a bit tricky, but and we need to be careful that we don't create a feedback effect here. But let's put this in here and let's see what's in there. It's a list of items which we can specify as an output. So if, for example, if we want to know more about the wind speed on our model, then we can put this in here. We can cite wind speed. We can put this in here as an output name, and that's going to be part of the output of our simulation. And that way we can actually look up what we want to look for and be very specific with what we want to actually look at and check and analyze. There's a lot of stuff in here, and most of it I have no clue what it is. So I think I will need to start studying more. more engineering stuff. But yeah, so you could then have a panel and add your specific type, specific item. For example, fan, heat, gain to air. And that I can then put into here. So this is what it's this for. And then we have another thing, which is the read zone sizing. This is a more straightforward thing. There's a separate output. It's called set as set for zone sizing, I guess. And it gives us the cooling load. Again, we need our translation tool. I mean our tool where we can separate the header from the values, and a panel. Here my cooling and my heating. Of course we can again read, parse a zone sizing CSV's result file from an energy simulation to get data collections for the cooling heating load over the peak design day. And if you're not 100% clear, the values are always for each zone, right? So I could basically go here and add the values here and look at the zones and the output together, and then you get a bit of a better understanding what that could be or should be. Okay, I think this is all I can really tell you about results. Now the best way to continue on that is to try it and use it, and that for sure then you will learn more. Nevertheless, so there's a bigger chunk we need to cover. This is these three parts: the Honeybee Adaptive Comfort Map, the Honeybee PMV Comfort Map, and the Honeybee UTCI Comfort Map. Let's try that. I placed this here, and let's see. Now, what do we need? Okay, we have our model. That's okay, but what we need for sure is this Honeybee model for which adaptive comfort will be mapped. Note that this model should have radiance grids assigned to it in order to produce meaningful results. As you can remember from Honeybee Radiance, that we have this tool here, Honeybee sensor grids from rooms. We can use that, so we can get all the rooms. We can specify the grid size. Let's do 1 meter, or maybe do 0.5 maybe. Model is in meter. That gives me this. As you can see, I have all my grid points here in the grid, and then we want to apply that to our model. Assign grids and views. Assign grids and views. So we need to get the model and the grid. The views we don't need because that's done by something else. Now we can then attach our model. So we should be now able to attach our model here. We need the E plus weather data, which is here. I push this a bit further out. E plus weather data. We need the design days, which was this file here. There is run settings and run. That's what we need. So these are mandatory, and you can play with the other things, but again, there are like radiance parameters, there are run settings, solar body parameters. This is always just be very specific. And my battery is over. Okay, doesn't matter. You're gonna see my TV. You don't need to see me really. We can just continue here. So we have these are mandatory. As you remember, always remember, underscore means mandatory input. Underscore at the end means it's not mandatory. You can input something, and if there's an underscore at the beginning and at the end, it is mandatory, but it has a default. And then run. This is what we also need. So, but yeah, I mean that's already what we need for this. And we can use the toggle here, Boolean toggle, and put this in here. Now it's calculating. Now it was finished, but of course you can't see anything because we still look at the grid stuff. If I want to go back here, it ran and we have outputs and we can look at the outputs. Report, there's nothing in there. Operation temperature, it's in here. Condition in here. A folder containing the CS map of the degree Celsius from the adaptive comfort neutral temperature. So these are all just links to the output. Here we have some output. The TCP list of values between 0 and 100 for the thermal comfort percent. These can be plugged into the Ladybug spatial heat map component along with meshes of the sensor grid to visualize spatial thermal comfort. TCP is the percentage of occupied time where thermal conditions are acceptable, comfortable. Occupied hours are determined from the occupancy schedule of each room. Any time where the occupancy schedule is 0.1 or larger than 0.1 will be considered occupied. Outdoor sensors are considered occupied at all times. More custom TCP studies can be done by post-processing the condition result. So it says you could use the thermal heat map from the Ladybug tools, which is this one, spatial heat map. And for that we also need the mesh or the meshes, let's say, which are here. This is the mesh, this is the grid. The grid points are all combined into one list. It's all flattened into one list. And we should do the same for the mesh. Oh, that was not a good idea. That was not a good idea. Now it's calculating everything again. Okay. Still no visual contact here because we haven't connected anything, but I flattened the meshes. I think probably I not just need to flatten the mesh, I need to combine the mesh. So I need to have this tool here, mesh, join meshes. That's what I need, because otherwise we get a problem because we only can put in one mesh, I think. So that means because we have only one list with oh no, we have several per room, but then maybe we don't need to flatten it. But let's see. Values, we put the values here and the mesh is here, and now of course it doesn't work. I'm doing this different now. I extract the data because that allows me to work with the data separately from the tool. Otherwise it continuously starts to recalculate everything, and I will do the same with the mesh. I just add an in-between tool here which is called mesh, and then I don't have that problem. Here also turn off this one. Now again it's calculating again. It was a bit of a mistake. So I know that I have 700 values, but currently it doesn't match with my spatial heat map. It doesn't work. I have the meshes here, so the data tree probably looks different, and maybe because if I put this in here, it's the same. It just doesn't work. So okay, how to solve that? 13 meshes. That's the problem. So I have different. My data is different structured. That's the issue. If I flatten this, it doesn't really change anything. If I combine it, then it becomes one mesh. Right, so that it's one mesh with 789 faces, and here I have 789 values, which would actually, it should be fine. So let's try to flatten this, and then it works. Yes. So I need to flatten it because, just show you very quickly how you solve that. If I look at the data tree, there's a tool, parameter viewer. So if I look at the data when it's not flattened, I can go in here and I can draw a tree. So I have for each of the different rooms, I have a separate list of data, right? If the problem now is that if I just add my meshes, if I put this in here, I only get one. Hoppla. Maybe if I don't, I get one. I have 13 values, which is in one list of it's inside one of these combined lists. It's basically a list within a list within a list, and here it's just 13 lists with values inside. So that's why it doesn't match up. If I flatten that, I would get one big list with all the values, with all the 789 values. And the combined mesh also works like that. The combined mesh is also just one list. It's a bit different organized, but it basically is the same. You get a mesh which has 789 faces, and these faces are collected here and assigned a color. That's it, and that gives me an output. And now I could, of course, close this grid. I don't want to see the grid. I also don't want to see the meshes on top of it. We have the meshes twice. So we have the mesh here, turn this off, and also this one. Then it's much more clear. What does 100 mean again? Let's read this again, because I think it's not 100% clear. The TCP, okay? List of values between 0 and 100 for thermal comfort percentage. It's basically in percentage. From 100 means 100% and 0 means 0%. This can be plugged into the Ladybug spatial heat map. That's what we did. Component along with meshes of sensor grids to visualize spatial thermal comfort. The thermal comfort percentage is the percentage of occupied time where thermal conditions are acceptable and comfortable, meaning in the areas where 100% of the time it's comfortable. That's a bit, I am not sure. It's the percentage of comfortable time in that space. That's actually interesting, because here these are not as successful, so they have a certain time where they're not that it's not that ideal. What else do we have here? We have the HSP, heat sensation percentage, a list of values between 0 and 100 for the heat. We could put these next to each other, by the way. It would be interesting. So, oh no, maybe this is a bit difficult, but let's do this. Let's see how it changes. So it's basically the heat stress and the cold stress. So this is the time, the percentage when it is acceptable. This is the heat sensation percentage, like time when it's actually not very nice because it's just too hot in this spaces. And also it's again in percentage, meaning 24% of the time it's not very nice. Actually, you can read that already from here. When I see these areas, I can already see, okay, it's only 75% of the time it's comfortable in these spaces. That means it's either too cold or too hot. So in these areas, it's could be too cold. So I could now, I mean, if with that knowledge, I could actually say, well, actually, my bedrooms are not placed the right way. But then at the same time, it's probably during the daytime when it's too hot. Might not be that of a big of a problem. And what's happening here? It's a bit of an issue. Cold sensation percentage. So we have very little cold percentage perception. But yeah, it just tells me that it's never the cold. There's never a problem with coolness. It could be also that there's an issue with that tool, because it doesn't give me a nice spatial heat map. I mean, this gives me a nice gradient. This gives me a nice gradient. I would expect something similar here. It is very little, probably, but is it really that small? Anyway, that's this one. There is another tool here we could test, we could try. Is this read thermal matrix and visualize thermal map. So what I did now here is to, instead of reading these things, these items here, I tried to use this, especially visualize the detailed result of thermal mapping and analysis from a comfort matrix. So it should give me a similar output. However, it looks, let's see what it means. So folder containing the CSV map, of the degrees Celsius from the adaptive comfort neutral temperature for each sensor grid at each time step of the analysis. This can be connected to the Honeybee read thermal matrix component to parse detailed results in Grasshopper. This can be used to understand not just whether conditions are acceptable, but how uncomfortable, hot or cold they are. So I guess it's pretty good, meaning that there's not a lot of heat and not a lot of cold stress. So it's always pretty much in a very neutral position, meaning 0, +1, +2 degrees. Let's see here again. Let's read more. Read the detailed result of the thermal mapping analysis from a folder of the CSV files output by the thermal mapping component. Detailed results can be temperature, AMD thermal condition results. It also includes metrics that gives a sense of how hot or cold conditions are, like PMV UTCI category or adaptive comfort degrees from neutral temperature. Yeah, again, so I guess it basically you assume a certain comfortable temperature, let's say 21 degrees, and whatever is above or below then feels too hot or too cold. As we saw already in the thermal comfort percentage, that we turn this on again, maybe this off, that most of the time it's pretty good. Here you have 100%. It's always in the right temperature, which sounds a bit unrealistic, but let's turn this off again and this on. Also have legend parameters where I could change the colors, and let's look at this. Yeah, it's very hot. Again, condition, it gives us the same output, just in a different way. Operational temperature, it's the same. So you could use it, we could look at these CSV files and understand which areas are neutral, which are too cold, which are too hot. Pretty straightforward. Operational temperature is another output here. Interestingly, it gives a different color scheme. It has a different color scheme, and it's interesting in a way that actually 23 degrees is that really that comfortable. A folder containing CSV maps of the operative temperature for each sensor grid at each time step of the analysis. This can be connected to the, again, component to pass detailed results in Grasshopper values are in Celsius. Anyway, so we get a lot of information out of that model. Okay, the next one in line here is the PMV comfort map. Again, we have similar input. Again, we need the radiance grids assigned, so we have done that already. So we can just take this model here. We again need the E plus weather data. We already have that. And we need the design days again, which came from here. Again, the design days are part of the weather data, the download weather data tool, which has the design days. North, run period, right setup map, airspeed, metabolic rate in the metabolic and our data collection, clothing level. So it's something similar, but a bit more specific, I would say. Compute spatial resolved operative temperature and predicted mean vote thermal comfort from a Honeybee model. This recipe can also compute standard effective temperatures. This recipe uses Energy Plus to obtain surface temperatures and indoor air temperatures and humidities. Outdoor air temperatures, relative humidities, and airspeeds can be taken directly from the E plus weather data. The energy properties of the model geometry are what determine the outcome of the simulation, though the model's radiance sensor grids are what determine where the comfort mapping occurs. Long wave radiant temperatures are obtained by computing spherical view factors from each sensor to the room surface of the model using radiance. These view factors are then multiplied by the surface temperature output by Energy Plus to yield long wave MRT at each sensor. All indoor shades, those representing furniture, are assumed to be at the room average mean radiation temperature. A radiance-based enhanced two-phase method is used for all shortwave mean radiation temperature calculations, which precisely represents direct sun by tracing a ray from each sensor to the solar position. To determine thermal comfort percent, the occupancy schedule of the energy model are used. Any hour of the occupancy schedule that is 0.1 or greater will be considered occupied. All hours of the outdoors are considered occupied. Okay, it's something very similar. The output is very similar as well. Similar, here we just need to run it again. It's just a different method. Okay, that went through. So we can use the same method on looking at the output. I want to make a, well, I will just close this here. And I want to preview this again. That was interesting. Okay, we can use the same, just we can reuse whatever we have here because it's the same method. Just plugging in these items. Again, I will do the same here. I will just put my stuff in here and we already have the result. It's very different. It's a very different result. It's very strange because, I mean, if you look at this, it almost feels like, okay, most of the areas are comfortable. It gives us a different view. And it has, again, this is very similar, I guess, the heat, spatial heat percentage, heat sensation percentage, we also have that here, and the cold sensation percentage. Very interesting. It's a very interesting, very different. Here I'm feeling there's something wrong anyway. It's very interesting that it's so different. We again can use at the predictive mean vote for each sensor grid. Let's check that out. I want to know how that will look like. This will calculate a bit. Okay, so that was finished calculating. Let's get the preview here. So that's very similar. It's very similar. Most of the time it's neutral, slightly cold in the other areas. So the kitchen is neutral, the rest is slightly too cool, slightly cold. So yeah, okay. Again, you have the condition, it's very similar, temperature, condition, and the predicted mean vote. I mean, sometimes I feel like, why does the names have to be so complicated? Okay, now, last one left. So this is going to be a bit different because it's the UTCI and this is about the outdoor comfort. Again, it's the same method. Design days, E plus weather file, and the run button. But again, in that case, our model need to have a ground, and that's the problem. So in a way, we could. Is our ground, okay? We need to add this, so we need to create a new room. We need to have Honeybee face and the geometry. So this is a surface, or let's say a poly surface. Put this in here, okay. Face, yeah. In order to make this work, we need to actually extrude that. Okay, extrude. This is my ground. Now I need to reconnect that because it didn't work. And now I could add this to my rooms, but what I do in order to I'll create a new set of grids. Right, so I will do this, and this is not a model for my indoor stuff, and I created a new model which is my outdoor stuff, and I only assigned this room with the grids. So let's look at that. So I hope you understood that move. So I have this model. This is my indoor model where I assigned all the rooms with the grids, and then I add the grids to the model, and then this is my new model. So this is basically don't need to look at because it's not used. Now I added a new room, which is not a room, it's actually the soil. It's this bit here. Yeah, I placed here my placed here my room that goes into here. I think I missed the point, and actually I need to add one more item. Honeybee, this honeybee ground that I need to now. Honeybee knows that this is the ground. That's what I need to do. And I put here soil name, and now I can place this, and now it should work actually. Again, I will turn off the grids here, and also the room itself. Don't need to see this. I don't need to see this, really. Oh no. Okay, now it should be fine. So again, I calculated this here. Now I should see if I connect this now here to the spatial heat map, then I should get here all the. So I could connect this here, and of course now I have a different mesh. So I need to get the mesh from here. Yeah. I can turn this off. So this is again very similar. Again, it's the same concept. I can look here now. It's really exactly the same output. So we have the thermal comfort percentage. This output means that 28% of the time at the blue areas is comfortable. 33% of the time it is comfortable at the red areas. Cold stress is actually not as much, whereas we have heat stress 70% of the time. It's interesting. Sounds a bit too much for me, to be honest, because it's London. It shouldn't be. So we need to explore this a bit more, because I feel like there's a bit of a. Seems like it doesn't really work. This seems to be a problem. Anyway, let's look at the matrix output, because that maybe gives us a bit more clue. So again, we can plug in the category here instead. Oh, mesh. The mesh is the wrong mesh again. Sorry. And I can turn this off and this on. Slightly cold. It's that doesn't make any sense to me. Category. Oh no, +1. Yeah, -5 is extreme cold stress. Okay, it basically divides it in categories. It's always just a little slight cold stress. That I believe it's actually more cold than warm, but it's never really that cold here in London. Heat. Okay, and then we have condition, acceptable, unacceptable, neutral. Let's put this here. So it's between neutral and cold most of the time. So I would agree with that. So it's more cooler than, but it's between neutral and cold. I would agree. That sounds very much like London. If I look at the annual time. By the way, you can add a run period, so that could actually help you to look at different months. UTCI, let's see, because that feels a bit strange. But yeah, let's see what comes out. The UTCI is the perceived temperature. It's not the real temperature, it's the perceived temperature. Again, this is a bit strange. I don't believe that it's 6 degrees as an average and 4 degrees as an average. That's relatively cold. By the way, let's turn off this here. I don't want to see that now. I mean, we could test that. We could compare that. Now, okay, I will do that because it gives us some output. The UTCI is the perceived temperature, and it's calculated from the temperature, the wind speed, and humidity. And even though the temperature might be 18 degrees, because you have a breeze and it's very dry, you might feel it's much colder. So, and this is an average over the annual, the whole year. So it is warmer next to the building, which is, it's already interesting. That I want to test more about that. Probably in the next future videos, I will test different scenarios to really understand how the building influences the outdoor. Let's say I think next time we build a very simple model, just one room, we give it different materials and see how that affects the outdoor. That would be really interesting. That interests me most. But we could we could compare that with the UTCI, the general UTCI of London, by just doing this. UTCI, where is it? By the way, here's the calculate predicted mean vote. is a thermal comfort model for use on the interior of buildings where heating cooling systems is operational. Note that for natural ventilation buildings, the adaptive thermal comfort model should be used. Okay. That tells us something. The PMV comfort should be used if we have a different heating cooling system. Maybe that's why it has a very different output. So I think, although this will be the last video to conclude this this series, but then we might look at some things in more specific. But yeah, we could use here the Ladybug UTCI comfort, and for that, wait, let me check. For that, we need just a few items from our. So we need two items. We need the Ladybug import weather file, so we can add the weather file here, and we need the Ladybug UTCI comfort. We have air temperature, which is the dry pulp temperature. The meantime radiation temperature, that we would need if we have now a building or something, which adds shading. I will not use that for now. I just want to get a very draft overview of London, basically, without taking any buildings into account. Relative humidity and wind velocity, which is the wind speed. And then we can run this. And now we could, so we can separate this. We can first of all get the UTCI. This is the UTCI is the temperature, and we get these values here, all the hours of the year, and we could average this to get one output. Yeah, actually, seems like it is very similar to this. Yeah, I'm surprised. So you can actually see here, this is the perceived temperature. Again, it's not temperature, it's what you feel the temperature is, and it could be much warmer. The temperature could be more because there's a wind, it feels much colder. That actually makes quite a lot of sense if I compare this. So next to the building, probably there's less wind, and there's some radiation coming from the building, meaning that it's warmer next to the building. Interesting. Okay, I think that concludes quite a lot. Yeah, hey, this was the last video for this series, looking at thermal matrix, thermal output, comfort, indoor and outdoor comfort, which is actually what I want to get to the whole time. So we basically worked our way all the way the last few months, and of course it could be much faster, but I also need to learn and look at these items closely to understand. But yeah, so we have reached the end, but the end is just the beginning, so there will be more, of course. So just very quickly, as a bit of a teaser, I want to look at a lot of things. One is the lunchbox, that goes a bit into machine learning. I'm very interested in machine learning. Of course, we will look more in the Ladybug tools, but in that case, Dragonfly. So how can we use what we learned from Honeybee on larger scales? That interests me most. Because I'm a landscape architect and urban designer. That's what interests me most. Is climate on a bigger picture. There's still some stuff we need to finalize in Eddy 3D. There's things which I want to check. There is also Butterfly, of course. We still have to look at some of the items, but I want to conclude it a bit because I'm really hoping that the developers will finalize that tool at some point and maybe even upgrade it so we can use it with the latest Blue CFD tools. But yeah, there's Octopus, there is all kinds of stuff which I want to check. And if you have any recommendations, or if you have specific questions about any of the tools in Grasshopper, then let me know. I'm always up for learning more and look at these things from my perspective, and then you can add your own perspective to it. That's how I would move forward. And yeah, thanks again, everybody, including my channel members, which is Rusheng Yang, Rafael F. Giaretta, and Mohsin Hassan, Combo 45. Melvina is gone, sadly, but that's how it is. That's how life is. Hope she will come back at some point. You never know. Anyway, thanks again. Thanks everybody for being part of it, being part of that series, and I will see you in the next, hopefully also very interesting Honeybee, Ladybug, or whatever kind of series. See you next time.